In this video, we will learn how to recognize and successfully complete a ring expansion. Keep in mind that this video does not explain which reactions result in such expansions. There are three main rules. Number one, the carbocation atom must be directly attached to the ring, not on the ring. Number two, a ring will only expand up to cyclohexane, which is a six-membered ring. Expansions can occur from 3 to 4, 4 to 5, and 5 to 6. And last, number 3, ring expansions happen before hydride or methyl shifts. Let's look at some examples. Which molecules below will undergo ring expansion? Let's start from the left at the cyclobutane. The carbocation atom, which is highlighted in pink, is directly attached to the ring represented by the maroon carbons. This molecule is eligible for ring expansion from 4 to 5. For the next molecule, again, the carbocation atom is highlighted in pink and is also directly attached to the ring, which is represented by the maroon carbons. However, since the molecule is already a six-membered ring, it will not expand to 7. This is because six-membered rings are the most stable, and the molecule doesn't want to break itself to form something that's less stable. The next molecule has a carbocation, again in pink, directly attached to a 5-membered ring, and so this is also eligible for ring expansion. It will expand from 5 to 6. For the last molecule on the right, unfortunately, the carbocation is located on the ring itself, and it's one of the maroon carbons. Therefore, this molecule cannot undergo ring expansion. Of the two molecules that can expand, we will work out the ring expansion of the cyclobutane in the space below. We begin with the carbocation atom and number 1, 2, 3 around the ring as shown. We also draw in the hydrogen on carbon 2 since it will help us visualize the rearranged structure later. To expand, we show an arrow taking the pink electrons between carbons 2 and 3 and attach it to carbon 1, the original carbocation. Because carbon 2 lost the bond with carbon 3, it now only has 3 bonds and therefore becomes a carbocation. Since the original carbocation at carbon 1 gained a new bond with carbon 3, its charge is now 0 since it has 4 bonds. The new structure looks awkward, so we convert it into a proper 5-membered ring as shown by the dotted arrow. The dotted arrow does not represent a step in the mechanism. Instead, we simply redrew the structure, and we use the pink numbers to help us track the molecule during the expansion. Now, this next part is extremely important because all ring expansions are followed by a hydride shift or a methyl shift. In this example, we have a methyl shift, and I've drawn the mechanism arrow in blue. The reason why we have a methyl shift is because we have a secondary carbocation that is adjacent to a quaternary carbon. I've highlighted the 2 electrons in orange for the methyl bond to show the group's transition from carbon 1 to the carbocation at carbon 2. After the methyl shift, carbon 1 has lost a bond and therefore has become a carbocation. Carbon 2 is no longer a carbocation and now has a formal charge of 0 because the carbon has 4 bonds. I've cleaned up the structure to show what you would need to draw on an exam that involved a ring expansion followed by a methyl shift.